Okay, so today we're going to be looking at different fluid flow and the effect the Reynolds number has on the velocity profile. And we're using Ansys. And I already started with the rectangle. Our constraint for this was that the length of the rectangle had to be, or the pipe rather, needed to be 150 times the height. So this is a very long rectangle, as you can see, but the height is 20 and my length is 3000. Um, so the step that we're on now, we're on the mesh. Um, so here we have the mesh, or we're about to start the mesh. We're gonna go normal to the XY, and as you can see, nothing is currently done. So we're gonna start meshing. Meshing honestly takes the most time, but we'll try to speed run through this. We're gonna apply this method here. We're gonna generate that, and then we go back to mesh. You're gonna see that it's divided now, and then we're gonna do another mesh, and we're gonna do sizing. And then for this, we're going to do the edges, the inlet and the outlet. So I'm going to resize this to fit the screen first so that I can capture both at the same time. That is a lot more. And what we're going to do is we're going to select the edge tool and hit Control. We're going to capture the inlet and the outlet. And we're going to apply the geometry. And then I'm going to change this to number of divisions. For this, I honestly have just been using 100. I'm just kind of feel like it's a good choice to divide the pipe, the inlet and outlet of the pipe by 100. And you'll see what that means in a sec. We're going to take the capture curvature off. And then for the behavior, we're going to change it to hard. And generate this. And if you go back to mesh, you'll see that it's starting to divide the inlet and outlet up by 100. And even by going to the outlet, should do the same thing. And it looks very just even. And towards the top, it looks like it has a little space, but it's fine. All right. Now we're going to do the same thing to the top and bottom plate. So we're going to go back to mesh. We're going to do another sizing. And here, we're going to grab that tool again, and we're going to do the top and bottom plate. So Control, top and bottom, and apply the geometry. Going to change that element size to the number of divisions. Being that it's 3000 millimeters long, I'm going to just do half of that. I'm going to use 1500. And then we're going to do the capture curvature. We'll see how 1500 looks. No capture curvature, and we'll change the behavior to hard. Yeah, I'm just gonna generate this. Actually, yeah, let me look at it in the mesh first. I was gonna say I was gonna go back and change it, but just look at it in the mesh. $15. All right, so doesn't look bad. This is pretty decent spacing here. Everything looks pretty even from what I can see. All right, so what I'm gonna do is now I'm gonna fix up those edges for the inlet and the outlet because they look horrible. So we're gonna do another mesh, and we're just gonna insert, and then we're gonna do face meshing. Take the rectangle, apply it, and then generate it. It should take care of all that. Go back to the mesh. It's gonna look black. Grab this. But as you can see, it looks very nice in the middle like before, and now the edge looks really clean. The last quick thing that I'm gonna do before I leave out of here is I'm just going to name each part. So inlet, let me do the outlet. So for doing this, you're just clicking the part that you're trying to name, and then you're just going to click N for name. Just do this outlet. Let me grab that top plate. I can just do it here. Top surface. Bottom surface. Swell. All right. So pretty much good. You can see all the names of everything. Top, bottom, mesh. So now we're going to jump into the setup. We're just going to wait for everything to load. For me, or not for me, but we're doing 2D and then double precision. For me, my CPU is very powerful, so I'm going to up the amount of solver processes this thing can handle. Back. So what it was that I forgot a crucial step. So before you guys even start the setup, you're going to see a little logo here that looks like kind of like a lightning bolt. And you're going to right click and then you're going to want to update. This logo is going to show there because you want to update the mesh so that it transfers over to the setup process. And in the setup process, instead of this question mark, it'll actually have like a startup logo. So I went ahead and went back and did that. For you guys, it'll show this lightning bolt logo right there for the mesh. You'll want to update that and then go to setup. So I ran through everything and I was wondering why my stuff wasn't there. So what we're going to do is now we're already in the setup. So we're just trying to, so this is the actual fluent simulator in which how we're going to be able to, dictate the different flows, whether they're going to be in Couette or Poiseuille. So we're just going to play around with some of the values in here. That way we can go ahead and simulate those flows. So the first thing that we're going to want to do is we're going to want to go to our viscosity. And we're going to make sure that we have it in laminar because everything that we're doing is laminar flow. And we're going to hit OK. So viscous laminar, that's perfect. And then for our material, this is where we're going to select the fluid that we're using. It's already going to have air here. For me, since I'm creating a fluid, just because our case is already, very odd. Like this pipe is very, very long. So I thought, you know what, I'm just going to create a fluid as well, just to make things, just a little bit cooler. So I'm going to do like in semi-viscous fluid, something that has, that is a little bit more interesting. Let me change the values first. Let me do. So basically, I just put this information up online. I pretty much got like what I have here, engine oil. So we're going to change and create so that it actually duplicates this and overrides it. And we're going to close. And then if you go back to fluid, you're going to see engine oil is there and not air. So if we open it again, you'll see that we have the constant for our density and then we have our viscosity. All right. So after that, what I like to do is just check the cell zone condition and then see that the actual fluid that I just created and shows is actually being used. So we're going to go ahead and apply that there. Should already be applied, but I hit apply again just to make sure. And then we're going to go to our reference values. And on our reference values, we're just going to make sure that everything is lining up. So we're doing everything from the inlet. So we're getting all our values for. So what you want to make sure is that the density value that you plugged in, if you're creating a new fluid or if you're editing the values from that fluid, you want to make sure that the density is here and you want to make sure that the viscosity is here. I'll get into it in a second for the boundary conditions, but you just want to make sure that that's there. And then if it's not showing, if you updated it in the fluid and it's not showing there, what you can do is you can kind of open up to another area on the pipe and then go back to it and it should update and refresh. And I'll show you what that looks like now because we're going to go back actually into the boundary conditions. So the first we're doing is Poiseuille flow, which as you guys know, Poiseuille flow is going to try to produce some sort of parabolic velocity profile due to the no slip conditions on the top and bottom plate affecting the velocity coming in. So what we're going to do is we're going to click on inlet and then make sure that our type is velocity inlet. And then we're going to edit this. And then as we edit this, we want to add a velocity. So for me, with the fluid that I chose and just all the dimensions that we have at stake here, with the pipe being so long, I chose 0.25 as my velocity, just because we want that Reynolds number to be very, very small. And as you guys know, the formula for the Reynolds number is the density times the velocity times the hydraulic diameter divided by the viscosity. To keep the one way to keep that Reynolds number low is to have a very low velocity. So that's why I chose this. And it's small, but it's not too small to where the flow isn't there. So we're gonna go ahead and apply this as our boundary condition, and we're gonna close it. And then we're gonna also just double check that everything else is the same. This is for our interior. Oh, that's our interior body surface. Sorry. We're gonna edit the wall. Make sure, because these are walls here. Bottom and top surface should say wall, and it should say stationary because it is stationary during Poiseuille. Then we'll go to the top surface. Make sure it's wall. No slip, and then stationary. And then for the outlet, it should just be a pressure outlet, and there should be no values inputted in here. And you just leave everything how it is. So then now, what I was talking about before with the reference values, we're just gonna click on the reference values again. And now, so you see how our velocity isn't taken into account here yet. What we're gonna do is we're gonna go out and just change to like outlet for a second, and then go back in and then it should update to 0.25. And then the next step that we're gonna do is now we're gonna initialize everything. We're gonna drop down to initialization, and we're gonna keep it. I kept it as hybrid, and we're just gonna initialize it, and it's gonna run through what 10 iterations. Yeah, so it's just gonna say it's done. Your computer's slower, probably take a little bit, and then we're gonna hit run. And for me, I like to do 500. I've tried it with 200. 200 isn't bad either, but I'm doing this for the graph that is going to pop up. For the residuals, I'm doing this so we can get as much data as possible. So I'm going to go ahead and hit calculate. And then you are going to see that everything is going to just run. So you're seeing here, everything ran pretty much did pretty quick. Now, if you're running the simulation and the console is running extremely slow, it could be one of two things: your computer's slow, or the other thing is that the values that you chose, like whether the fluid or the type of pipe that you're having everything flow through, is kind of like either unrealistic or it's just very hard for the computer to simulate that type of flow. So it'll tell you, like, it'll say something like, oh, initializing or adding values to like smoothing out the process. Like it'll say something along those lines where it's basically initializing or adding values to try to compute what's going on. But for us, obviously, load it up quick. So for us, you see, this is what Poiseuille flow, pretty, steady decline here. So this looks good. What we're gonna do now is gonna add our velocity vectors. So we're gonna go to vectors. We're gonna go to a new one. We're gonna do velocity vector, and then we are going to compute it, and our values are gonna come up here, and then we're gonna save it and display. And this is where our pipe is. We're gonna close this here, and yeah. So this is, we can see that boundary layer forming. So this is Poiseuille flow once again, and this looks really good. So we'll leave this as is, and then what we'll do is we'll jump out here and we'll look at the results. Sorry, my AirPods had died. I have to charge them, y'all. But now, all right, so we're at the results. So we're just gonna open up the results and we'll wait for this to load. So now with the results, this is pretty much how we're gonna be able to just view our velocity profile. We're gonna basically see the contour to make sure that we are simulating Poiseuille flow properly. The first thing, just go normal. What we're gonna do is we're gonna go to location here, and then we're gonna do line. And then this first line is going to be the midpoint. We're gonna add 2 lines because that's basically where we are calculating our flow. That's where we're looking at the velocity profile from the midpoint and the endpoint. So the first one we can do is midpoint. And then this point is being that this is in meters, by the way. So we know that the pipe is 3,000 millimeters long. So half of that is 1,500 millimeters. And then if you do that in meters, it's 1.5. And then this is also going to be 1.5. And then what we're going to do is for the 0.2, this is basically the height of the pipe. So we're going to do, it's 20 millimeters. So it's 0.02. And then we'll leave it at 10 samples. Or actually, up it. I think the last time I tried this, I did 50. We're going to try 100 this time. Okay. So we have, you see the midpoint there, it's the yellow line. We're going to do it again for the endpoint. Now for the endpoint, it's a little bit different, being that the endpoint, for simulation purposes, the computer doesn't like, or the velocity profile doesn't like when you actually have the endpoint all the way at the end. So we're not going to put 3000 milliliters. What I did was I subtracted 1 or 2. So for this sake, we're going to subtract the 1, and we're just going to, or we'll do 2, and we'll make it into meters. So it'd be 2,998 millimeters, but we're in meters. And same thing for the height. We're in 02, and then we'll do 100 samples. And then you could see it's there, but honestly, oh, I messed up. I put 88. It's 998. Let's apply that. That was weird. And then, yeah, you see it's fixed. I'm like looking in just to make sure. All right, so now what we're going to do is we're going to go here to contour, and we're basically going to add the velocity contour so that we can have like we can basically see how the flow is. Oh, it isn't like dashes, so we'll just do contour. I'm going to put a dash in the middle. All right, so we have the velocity contour here, and we're just going to edit all this. So for the contours, I'm going to leave it at, I'm actually going to make it 10 so that you guys can see what it looks like with 10. And then for the labels, we are going to, or for location, we'll put it for symmetry first so that it's the entire shape. And then for the variable, as you know, we're in fluids, so we're using our velocity as u, and the range will leave it alone and all domains. And then the labels, we can leave everything else the same. All right, so we'll leave this at 10. We'll generate it, or apply it rather. And this is our velocity contour. So as you can see, these are all the values. But to clean this up and make it look a little bit better, we're going to go to the legend, and we are going to play around with this. So for the title, we don't really care about the location, so we're just going to change this to variable. And then we're going to make it horizontal, so it's up top. And we are going to change the appearance. So to make it a little bit, actually, I'll show you guys what it looks like up top first. This is what it will look like when it's up here. I think this is way better to see exactly what's going on, but you can actually increase the size. So we're going to make this, what is it, 0.6. So we'll put it to 0.8, and it'll be bigger. And these are the contours, as you can see, but to allow for it to match how the actual pipe is, we're going to go to the velocity contour, and I'm going to change the amount of samples to, let's see, if I did 50, get it to 50 samples. You can see it's kind of like it's a little bit smoother. We can even go to like 100 or 75. Then yeah, I'll show you 100. All right, and then what I'm going to do is, just so you guys can get a better picture of what's going on, I'm going to move. I'm using the pan tool to move, and I'm just going to kind of zoom in a little bit. But even with me zooming in, you can see how the boundary layer is forming when we come in at that inlet. And again, this profile looks like this. The boundary layer is like this because, again, our pipe is very, very long. It is very long and thin. So again, this is what the flow is going to look like with that. Actually, what we're going to do too is for the legend, what I'm going to do is for the appearance, I'm going to change the precision just so that it doesn't look so chunky. I'm going to make it a fixed point instead of a scientific form. That's better. So they have our velocity u. This is the contour, and this is how it looks in the pipe. So now what we're going to do is we're going to add a graph, or chart rather. We're going to go here to chart. We're going to change it to the velocity profile. And we're going to hit OK. So we want it to be velocity profile. I'm going to apply that. Yeah, we'll edit the data series first. Sorry, I'm jumping ahead. We're going to add 2 of these. So the first one that we're going to do is going to be our midpoint. And this is how we're setting up for the graph to compute the data. And what am I doing? Can't spell right now. and the location is going to be midpoint for the first series. Then series 2 is going to be endpoint. And we're going to, for the location, we're going to attach the endpoint to it. And then on the x-axis, we're going to have it be the velocity. And then for the y-axis, it's just going to be the y. And we're going to leave everything else the same. I'm just going to make sure everything looks good. Chart, into series, and we'll apply it. So yeah, this is the velocity profile for Poiseuille, parabolic as it should. And again, the reason why everything does look like this, as you can see, you can kind of see how it's like, you can kind of see this red here over the blue. It's really just because the pipe is so long that we are pretty much in fully developed flow with the length of the pipe. So in fully developed flow, this is how the velocity profile would pretty much look like. The endpoint and midpoint are pretty much like blended in. So this is what we have here. And yeah, this is Poiseuille flow. So we're done with Poiseuille flow. This is how everything looks. And all we're gonna do is just change it up a little bit for the Couette and then the combined flow. So all I'm gonna do though is just I'm gonna snap a picture of this. And then I'll come back and have a picture of this. Then I would grab my chart and I'll grab a picture of this. And then now what we're gonna do is we're just gonna go into our fluid simulator and then we're just gonna basically edit everything in here. So to go to Couette flow now, what we're gonna do is we're gonna go back to the fluid. We're gonna first do it with the fluid without touching any of the properties of the fluid. But now with Couette flow, we know that the top plate is moving with the velocity and it's coming in, and the fluid itself is coming in with no velocity. We're gonna leave everything else the same. The only thing that we're gonna touch is our boundary conditions. So I'm just going through the cell stuff just to make sure that we're still using everything that we're supposed to. Engine oil. We're gonna go to the inlet. We're gonna go to boundary conditions. You can just do it from here. And then we'll go to inlet and we're gonna change it from the velocity inlet to a pressure inlet. And we're going to make sure that this is 0. And then what we're gonna do is just kind of prevent, or no, we're gonna apply this here and close it. And then for the outlet, we're gonna edit it and then we're gonna do prevent reverse flow. And then we're gonna close that. And then for the top surface, we're gonna have the top surface move at a velocity. So we're gonna edit it and then now we're gonna make this a moving wall. And then we're gonna do no slip. And I'm gonna have it come in at the same velocity that our fluid came in at when we were doing Poiseuille flow. So now this should satisfy everything for Couette flow. Our bottom surface is stationary. The inlet is a pressure inlet with no pressure coming in, no gauge pressure rather. Our outlet, we just have it still as a pressure outlet, but we just prevent reverse flow. And then for our top surface, it's moving. So we should have a linear velocity profile. That's what we're aiming for, but we're gonna see if I need to play around with the velocity or either the viscosity in the fluid. Because I probably am supposed to up it a little bit. When I was running this simulation before, I had to up the velocity just to kind of get it. So what we're gonna do is we go to our reference values. Again, we're looking at it from the inlet. So we're gonna change out of it just so that the values can update since we're messing with things. And then now here, it should also be here. So we should have 870, 0 velocity, and everything should stay the same. And then now what we're gonna do is we're gonna left click on run calculation and we're gonna do initialize and calculate. And now everything is gonna run on the bottom here. And then if we go to our residuals for that, the hybrid is done. And then now calculating everything. You can see it running through here and its solution is converged. Everything is just loading. And it got that out the way. Calculations complete. Again, it loaded up fast pretty much because these numbers aren't giving me any issues. But again, if it's starting, if you see something in the console, it's going to say something along the lines of it's basically just adding certain things to try to smoothen out the process. Then you'll know that something is wrong. I would stop the calculation. There's a stop button here. I'd probably stop the calculation and then just change the values that you have just to get it to work. I'm just moving this up. So this is pretty much how it looks here. So what we'll do is we'll jump out of here. And then we are going to go to the results, and we're gonna update it. I know we had jumped back in, and then you see it even gave me the error that I wanted to refresh. So we jumped out of the results, and we're just updating it now with the new data that we had. That way we can jump back in, and then we should have everything there. So once this loads, it'll have the check mark, and I will just jump in. And yeah, so this is what it looks like. This is Couette flow. It's again, it's supposed to be pretty linear. And again, the reason why it's super linear right now, and we haven't touched anything luckily, is that Reynolds number is very low. Now it does like it's a little bit bent, but I mean, again, I chose to do, we're not using air or water. I'm using a pretty viscous fluid right now. So I know that's also playing a factor in here, but our radon number is still relatively low. I think with everything that I have, I'm coming in at about like a 90 for the Reynolds number. So that's pretty good. But if you definitely change the values and use maybe a like air or water, you could definitely come in with like a 10 or 20 and this would look super, super straight. But this is pretty much everything. We don't have to touch anything. And then you see our values that update here for our contour. And you see that boundary layer developing, and then you see how the top plate is moving and it is creating that linear velocity profile that we see in the chart. So this is really, really good. So what I'll do, again, your project, you just want to snap a picture here, then go to the chart, have a picture there. So what we're going to do now is look at the combined flow. So in combined flow, you have both the top plate moving and you're coming in with the velocity. That's going to be the combined flow for Poiseuille and Couette. So again, we're not going to touch our fluid. We're just going to come right back to the fluent simulation. I like to, again, just double check that the fluid is still there, because I have had situations where it did switch. And we're just going to change the boundary conditions. So we're going to go to our boundary conditions, and then we'll come back to the reference values to make sure everything is good. So for the top surface, we're going to keep the top surface moving at that speed, and then we're going to go to the inlet and change this back now to a velocity inlet. And we are going to, it already saved the value that I had before, so we're just going to use both. So they're both going to be moving at that speed, the top plate and the incoming velocity from the pump or whatever we have that's producing that. And then we're going to hit close, and then we're just going to go back just to make sure everything is good. I like to double check everything, better safe than sorry. Outlet should still be pressure outlet. We're still going to prevent that reverse flow. Then for the reference values, we're going to make sure that everything is coming in as it should. So for the inlet, we see that it's at that velocity, and then we're going to look at the top plate actually too. And then we're going to see that the top plate has the same thing, but we're going to go back to inlet because that's what we're computing everything from always. And then we're just going to go to the run calculation. We're going to initialize and calculate it. It's going to run through the 10 iterations, and then it is going to now go through everything here. So again, it should run relatively smooth. Just let everything, don't touch anything, just let it all run. And then we'll wait for the simulation to update. And we're gonna hit okay. And then you're gonna look at the residuals, and you can see this is how it's supposed to look. Downward slope, everything looks fine. And then this is how it's looking. So what we're gonna do is we're just gonna minimize this. And then again, don't forget to update. We'll come back in, update our results. And just wait for this to load. I really would highly recommend doing this on a computer that can run this software without giving you any issues. Because I mean, I can only imagine what this would feel like running on like a super slow computer. And here we are. So it automatically took us to the chart value, but this is how it's supposed to look, right? I mean, we have that incoming velocity, but we also have the top plate moving. So it's pretty much just like the Poiseuille flow, but our parabolic is our velocity profile with this parabolic format is a little bit stretched out, and it's obviously off the chart. If our chart was scaled a bit back, we could see it, but this is how it looks. This is how it comes in as. If we go to the viewer, everything updates and refreshes, and you can see that top plate is moving. We have the incoming velocity. You can see with how the contour and the gradient looks here. So we have that pressure gradient, and then we have that bottom plate stationary. So it's causing that flow here. Or let me go back to the chart viewer. Causing everything here. But yeah, so this is how the three flows are going to look. with a pipe of this size. And again, when we were looking at the Poiseuille flow, it really only did look like that for the midpoint and endpoint velocity profile due to this already being in pretty much fully developed flow. Now, if we had a very short pipe, like maybe like 100 millimeters or so, you would definitely be able to tell the difference between the velocity at the midpoint and the velocity at the endpoint, but not in our case. But yeah, this is pretty much how you guys are going to simulate this flow in Ansys. And yeah, hope you guys enjoyed. I hope I taught you guys something, and I'll see you guys next time.